get out your notes, and let's talk about this last thing, the mean value theorem of integration. The FTC, and MVT of integration. See, mathematicians don't like to write a lot of words, so we have a lot of symbology, right? Abbreviations. We like abbreviations. So the fundamental theorem of calculus and the mean value theorem of integration. The fundamental theorem of calculus, FTC, said that if you have the integral from a to b of f of x dx, that was the antiderivative of b minus the antiderivative of a. We know this already. This is what we talked about last time, right? This is, we find an antiderivative, right? We use our inverse power rule, or we memorize our list of antiderivatives, like the 1 over x is ln, and we plug in those numbers, right? Starting with the b minus the a. So this is our fundamental theorem of calculus. The idea that we can identify an accumulation of stuff, right? This integral is an accumulation. How much have we added together, right? How much have we gained over the course of time by finding an antiderivative and plugging in the difference, right? Where do we end minus where we start? This is basically, right, f of b is kind of like, you can think of this as like where we end. The amount we end with, where we end. And f of a is like where we started. And the integral is the accumulation over a to b, over that amount of time. How much have we gained? How much have we gained? Oh, shoot. Hold on, everyone. Hold on. Oh, they're not. There we go, everybody. Apologies for that. Here we go of what we're learning. FTC and MVT of integration, right? Like I said, we have a lot of abbreviations we like to use. And this is what we know already. This is what we know so far. Right? Our integral from a to b. What we have gained over the course of starting at a, like from a to b, the amount we have accumulated, is the antiderivative of where we ended minus where we started, right? That's the difference between those two things, is the amount we have gained. I mean, this is pretty irrefutable, a pretty irrefutable definition, right? If I started with 3 eggs, right? If I started with 3 eggs and I ended up with 12 eggs, I have gained 9 eggs. My accumulation is 9 eggs over time, right? The chickens lay eggs over a certain function, a certain amount per a rate of laying, right? A certain rate of laying. Maybe it's 1 a day. Maybe it's I have a certain number of chickens, right? Whatever my rate of laying is, from one day to the next day, from day A to day B, I have accumulated this many eggs, right? I started with this number of eggs. I ended with this number of eggs. The difference is how much I've gained. This function is, that's what this fundamental theorem of calculus states. One of the critical things about doing this is very important rearrangement. Very important way to rearrange this. Very important idea is the following thing. If I rearrange this, let's say I add the f of a, move it to the other side. If I have my antiderivative of a plus my integral from a to b, f of x dx, that's going to equal f of b. So what this is saying is where I start plus how much I gain, equals where I end up. This very important idea in AP Calculus in integration. We could take this fundamental theorem of calculus and sort of rearrange it, basically saying that if I know a starting point of a function, if I know where my function starts, and I know how much I've gained over some period of time, I know that at the end of that period of time, I will have a certain amount. Right? I mean, that's sort of hard to refute that. It's hard to deny that. So, for example, let me give you an example. If f of 0 equals 5, and the integral from 0 to 6 of f prime of x dx equals 9, find f of 6. For example. So what we're looking for, we know that this function f, some function f, at 0 is located at 5. Some function, so if we want to like draw this out, let me draw this out, a diagram here. If I know that some function f, this is f of x, at 0 starts at 5. I want to know where does f of 6 end up? That's what we're asking. Where's f of 6? Where's my graph gonna end up? I don't know what the shape of the graph looks like between 0 and 6. I don't know the shape. I don't know if it's like this, if it's like this, who knows, right? I don't know what the shape looks like. But I do know that if I have the derivative of f, and I integrate that from 0 to 6, this function has gained, it's increased, right, by 9 value, and the value of 9. It's increased by 9, right? This 9 is, because it's my integral, right, this here tells me that f increased by 9 between 0 to 6. The function f has increased by 9 between 0 to 6. And it's the integral of the derivative graph, right? I need the derivative here. This is my derivative. So the amount that's been gained between 0 to 6 of my f function is 9. I don't know what the shape looks like. I just know that it has increased by 9 over the course of this time. It could have decreased a little bit and then increased by more, right? I don't know. I don't know what happened between 0 to 6, but I know that over the course of this time, it has overall increased by 9. And so if you want to think of it like an equation here, I know that f of 6 equals f of 0 plus the integral from 0 to 6 of f prime of x. So this is going to be 5 plus 9 gives me 14. And that's the value of f of 6. Up here, it will reach this value of 14. Increasing by 9. That's a 6, by the way. And so we use this equation, we use this, this feature a lot. They use this a lot. This idea that if you know some amount in the beginning and you've gained some amount later on, how much do you have at the end? They use this feature quite a lot. And so here you were given the integral. Here you were given the amount of the integral. Sometimes you'll have to take the integral and do the calculation behind it, right? Do the math behind it. If you're given an equation, find the integral of that equation, right? Most of the time they'll tell you that's what it is, though. So this is one of the things, this is the fundamental theorem of calculus. Again, using this accumulation idea that you're gaining some amount over time. Again, we don't know how the graph looks. It could have, again, if I did the integral from 0 to 1, maybe it was negative. Maybe the graph fell during that time. Right? Negative integral, right? The graph is negative, negative slope here. And then maybe the slope is 0, and then maybe it was positive, really positive over here. Or increase, decrease, increase. Who knows what the graph did between 0 to 6? Who knows what the shape is? I just know that by the end of the graph, I have reached 9 greater. I've increased my value of f by 9. And so I have reached 14. I started at 5. I'm at 14 now. Okay? So that's one thing. Really quickly, the last thing, and I'll leave you to this assignment in a second, is the mean value theorem. Mean value theorem, that's what the MVT is, MVT, for integrals. The mean value theorem for integrals finds the average value of a function over time, over an interval. The mean, when you think of the word mean, right? Mean means average. The average value theorem, the mean value theorem for integration says, well, I want to know what the average value of some function is over a particular interval. The average value, meaning the average like y value. The average height of a function over some interval. Because a function goes up and down and up and down. If I want to know the average number across this interval, how do I find that? And it says if f of x is a differentiable on a to b, there exists a c where f of c equals 1 over b minus a integral from a to b of f of x dx. Let me make this a little bit better. So this is your mean value theorem here. And this equals the average, hold on, let me go like this. Where f of c is the average value of the function on a to b. So I know we're out of time. I just want to give you a picture here. So here's a graph of f of x, right? And say that f of x starts here, goes up and down and up like this, right? Say this is f of x. Over the course of time, right, if you try to average out, right, f is getting higher here and lower here and higher here, right? Somewhere along the graph is like, maybe like here, is some f of c value. This is the average of f. It's like the kind of middle of the graph, right? It's like the average amount of, you go up, you go down, you go up, like you kind of have an average amount here. And there is guaranteed to be at some point some value c where the graph touches that average. Maybe there's a couple, might be a couple, but guaranteed at least one. And that's what you find by using this equation. 1 over b minus a, right? The basically slope is the rate, it's the amount of change, right? The amount of change, how much have you gained, divided by the average b minus a. So here is a, right? Here is starting at some a, from a to b. On that average interval, there's some average amount where it fits in the middle of your function, where it's the average value of the function. So we will use this next time to find some of these averages. Use this equation. Your assignment, I've posted to Schoology. We are going to work on that, exclusively work on that project next class. That assignment next class in Schoology. But I'm going to open it up if you want to get started on it. There are a bunch of questions. We will do this practice using integrals in the fundamental theorem of calculus next time. So it's opened up on our handout here. You can view the handout here. There are, I think, 14 questions. Oh, goodness. So using the mean value theorem, we'll do that together tomorrow. And then lots of other complex questions involving accumulation and average values, things like that. Oh, 18 questions. Well, fine. Oh, goodness. Anyway, that's it for us. I know we're out of time. Thank you all for staying later. Tomorrow, come by for a review. Thursday, we will go over this assignment together and work on this together in class. Good luck, everyone.